Hello, I'm Lloyd G. Stovall from the Media Library. Our library specializes in unique projects, and today we're excited to share one of our latest endeavors. We've taken a genuine scientific project and challenged AI to transform it into a narrative. Please let us know in the comments if we've succeeded in our goal. First, you'll experience the story, followed by a scientific breakdown explaining the artistic expression. Thank you for listening. Now, let's begin with the story.
This narrative delves into the tangible creation of a generator that harnesses the potency of low-frequency energy. Our focus is on the art of transforming subtle ambient vibrations into a substantial electrical output. It's a testament to the principle of energy conversion, not amplification. We capture, channel, and elevate existing energy, rather than conjuring it from thin air. At the core of this invention lies a humble inductor, a conduit for energy's rhythmic dance. Its back-and-forth motion, a resonant ballet, induces an electrical surge. This surge, a fleeting moment of heightened potential, is meticulously captured and stored. We'll journey through an artistic interpretation of this process, followed by a scientific dissection to illuminate the underlying mechanics. Title: Tess and the Resonant Soul Generator.
The laboratory was more than just a workspace for Tess. It was an extension of her mind, a place where chaos was carefully woven into order. The clutter of metal and glass around her felt like a chaotic cosmos, yet she could sense the potential harmony waiting to be unveiled. Today, her task was ambitious: to transform a modest motor into a powerful frequency solid-state generator. Each component she selected, capacitors, coils, diodes, and MOSFETs, became an instrument in her symphony of engineering. She began with the capacitors, arranging them meticulously on her workbench. As she placed each one, C1, C2, C3, and so on, each slightly smaller than the last, she imagined them as a chorus of energy storage, each capacitor holding a unique note in her electrical composition. Her fingers traced the cold, hard metal, feeling the potential within. She connected them in series, forming a delicate dance of wires, each soldered joint carefully crafted to ensure precision. Between each capacitor, Tess introduced diodes and coils, components she considered the gatekeepers of current and the rhythm makers of her circuit. The diodes ensured that current would flow in only one direction, while the coils introduced inductance, setting the rhythm and delay. Together, they formed a resonant circuit, a system where the capacitors and coils would vibrate in unison, their energies oscillating back and forth in a harmonious balance. As she connected the components, Tess's mind wandered through the principles guiding her design. She knew that in a resonant circuit, energy oscillates between the capacitors and the coils. The resonance, a concept both beautiful and terrifying, could amplify the voltage across the capacitors, particularly the largest one at the end of the series. The thought of this tidal wave of energy surging through her circuit thrilled her. Next, Tess introduced the motor, a humble yet essential part of her design. It wasn't just a motor, it was the heart of her creation, with its make and break switch acting as a metronome of electricity. With each flick of the switch, the circuit would vibrate at a certain frequency, disrupting the equilibrium and sending controlled chaos through the system. Tess knew that this alternating current effect was crucial for tuning the resonant circuit to its optimal performance. The MOSFETs were the final components she integrated into her design, and they held a special place in her thoughts. These transistors were more than mere switches, they were the conductors of her will, shaping the raw energy flowing through the circuit. With precision, she adjusted the MOSFETs, knowing they would control the current flow and amplify the voltage, just as a maestro guides an orchestra through a symphony.
As Tess worked, her thoughts danced between the practical and the abstract. The mathematical principles guiding her were clear in her mind, yet they felt like melodies rather than mere equations. She paused for a moment, staring at her blackboard, where the key formula for resonance frequency was scrawled. 1. Resonance frequency, F. 1 2 TVLC Φ equals. This equation, she mused, was where the magic of resonance truly revealed itself. The input voltage, V_in, the resonant frequency Φ, and the input frequency, En, all played a role in determining how much the voltage could be amplified. It was a delicate balance, but one she was confident she could master. 2. Voltage across the capacitor, V. Then VL1 Φ fin.
As Tess fine-tuned her circuit, she could almost feel the energy building, a tangible force waiting to be unleashed. The laboratory grew quiet as she lost herself in the final connections, the anticipation building with each twist of wire and soldered joint. Soon, the first notes of her electrical sonata would resonate through the lab. Finally, the moment arrived. Tess flipped the make and break switch, and the circuit came to life. The resonant circuit, enhanced by the MOSFETs and the careful tuning of the components, allowed her to take a small motor and generate a substantial amount of voltage and current. The energy stored in the capacitors surged forth, amplified by the resonance, enough to power a small device. Finally, the moment arrived. Tess flipped the make and break switch, and the circuit came to life. The resonant circuit, enhanced by the MOSFETs and the careful tuning of the components, allowed her to take a small motor and generate a substantial amount of voltage and current. The energy stored in the capacitors surged forth, amplified by the resonance, enough to power a small device.
This complete story 1. Now let's get a bit more scientific in our explanation. Same story, but put in a more forward representation. In the heart of her cluttered laboratory, Tess, a brilliant young scientist, meticulously arranged her components. A collection of capacitors, coils, diodes, and MOSFETs, each piece was carefully placed to form a complex yet elegant configuration. Her goal was ambitious: to transform a modest motor into a powerful frequency solid-state generator. The setup. Tess began by arranging the capacitors in a series, each connected to the next by a delicate dance of coils and diodes. Here's how it looked. Capacitors in series. Tess lined up capacitors, C1, C2, C3, Cn, each one slightly smaller than the last, leading to a larger capacitor at the end. The capacitors were designed to store and release energy in sequence. Diodes and coils. Between each capacitor was a diode, D1, D2, D3, Dn, followed by a coil, L1, L2, L3. Lane. The diodes ensured that current flowed in only one direction, while the coils introduced inductance into the circuit. Resonant circuit. Tess's setup was a resonant circuit, a system where the capacitors and coils work together to create a resonance effect. Resonance occurs when the inductive reactance of the coils and the capacitive reactance of the capacitors match, allowing energy to oscillate efficiently between them. This phenomenon, known as resonance, greatly amplifies the voltage across the capacitors, particularly the largest one at the end of the series. The effect of resonance. Tess knew that in a resonant circuit, energy oscillates between the capacitors and the coils. When the circuit was tuned to resonate at a specific frequency, it created a powerful effect: voltage amplification. The resonant circuit allowed Tess to achieve higher voltages than the input. This was due to the energy being transferred and stored in the capacitors, amplified by the resonant frequency of the circuit. Back EMF. As the coils generated back EMF, electromotive force, they created voltage spikes that contributed to the increased voltage across the capacitors. Building bigger and better. With her basic resonant circuit working, Tess decided to build a more sophisticated setup. She scaled up the capacitors and added a make and break switch to her small motor. This switch, known for its ability to alternate the circuit on and off, played a crucial role. Make and break switching. This mechanical switch created an alternating current AC effect by rapidly opening and closing the circuit. It mimicked the behavior of AC, causing the circuit to vibrate at a certain frequency. This frequency control was essential for tuning the resonant circuit to its optimal performance. MOSFETs and voltage control. To manage the current and voltage more precisely, Tess integrated MOSFETs into her design. MOSFETs. These transistors acted as switches and amplifiers in the circuit. By adjusting the MOSFETs, Tess could control the current flow and amplify the voltage further. The MOSFETs worked in concert with the resonant circuit to handle higher currents and voltages efficiently. Mathematical insights. To fully understand the impact of her design, Tess delved into the mathematical principles. Resonance frequency, F. F0 equals 12 pi LC F_0 equals frac 1 2 pi SQRT LC. F0 equals 2 pi LC1, where LLL is the inductance of the coils, and CCC is the capacitance of the capacitors. This equation helped Tess tune her circuit to the desired frequency for optimal resonance. Voltage across the capacitor, V. VL equals VIN1 minus F0 fin V_L equals frac V_in, 1 frac, F_0, F_in, VL equals 1 minus fin F0 VIN, where VIN V_in VIN is the input voltage. F0 F_0 F0 is the resonant frequency, and Fin_in Fin is the input frequency. This equation showed how the voltage could be increased significantly due to resonance. The result, as Tess fine-tuned her circuit, she observed a remarkable outcome. The resonant circuit, enhanced by the make-and-break switch and MOSFETs, allowed her to take a small motor and generate a substantial amount of voltage and current. The energy stored in the capacitors was now enough to power a small device, demonstrating the power of resonance and modern engineering. In her laboratory, Tess proved that with the right combination of components and understanding of resonant circuits, even a modest setup could achieve impressive results. Her work not only showcased her ingenuity, but also provided a practical demonstration of scientific principles in action, blending artistry with engineering to create something truly remarkable. Certainly, the story of Tess and her resonant generator, while fictional in this narrative, is based on real scientific principles and techniques used in electrical engineering. Here's how the described phenomena work scientifically. 1. Resonant circuits concept. Resonance occurs when the inductive reactance, XLX_LXL, of an inductor coil equals the capacitive reactance, XCX_CXC, of a capacitor. This happens at a specific frequency called the resonant frequency. Mathematical formula: F0 equals 12 pi LCF_0 equals frac 1 2 pi SQRT_LC. F0 equals 2 pi LC1. LLL is the inductance of the coil. CCC is the capacitance of the capacitor. F0 F0 is the resonant frequency where the circuit naturally oscillates. Scientific explanation: at resonance, the impedance of the circuit is minimized, allowing maximum current to flow. This condition maximizes energy transfer between the inductive and capacitive elements, leading to high voltage across the capacitor if the circuit is properly tuned. 2. Back EMF and voltage spikes concept. Back EMF, electromotive force, is the voltage generated by a coil when the current through it changes. It opposes the change in current, creating voltage spikes. Scientific explanation: when the switch in the circuit opens or closes, it changes the current through the coils. According to Faraday's law of induction, this sudden change induces a voltage across the coil. These voltage spikes can enhance the voltage across the capacitors in a resonant circuit. 3. Make-and-break switch concept. A make-and-break switch creates alternating current, AC, by rapidly opening and closing the circuit, producing a pulsed waveform. Scientific explanation: the rapid switching introduces a periodic variation in current which can excite the resonant frequency of the circuit. This process converts DC from the motor into an alternating waveform, which is crucial for maintaining resonance and maximizing energy transfer in the circuit. 4. MOSFETs and voltage control concept. MOSFETs, metal oxide semiconductor field effect transistors, are used as electronic switches that can handle high currents and voltages. Scientific explanation: MOSFETs control the flow of current in the circuit. They can be used to switch the current on and off rapidly, modulating the power delivered to the capacitors and improving the efficiency of the energy transfer. They can also act as amplifiers, increasing the current to match the higher voltage generated by the resonant circuit. 5. Capacitor and coil configuration concept. Capacitors store electrical energy, while coils, inductors, store magnetic energy. In a resonant circuit, these components interact to transfer energy efficiently. Scientific explanation: as energy oscillates between the capacitors and coils, the circuit can achieve high voltages due to the energy stored and released in each cycle. The capacitors charge up during one phase of the oscillation and discharge during another, while the coils create a magnetic field that stores and releases energy. Practical implementation: building a resonant circuit. Choose capacitors and coils with values that match the desired resonant frequency. Use precise measurements to ensure the components are tuned to resonate at the same frequency. Enhancing voltage and current. Use MOSFETs to switch and amplify the current. Incorporate a make-and-break switch to generate an AC waveform that excites the resonant frequency. Handling back EMF. Ensure the circuit is designed to handle voltage spikes from back EMF, protecting sensitive components from damage. Conclusion: the story of Tess uses scientific principles related to resonant circuits, back EMF, make-and-break switches, and MOSFETs to create a high-voltage generator. Each element in the story, resonance, back EMF, and MOSFETs, plays a role in demonstrating how energy can be amplified and managed in electrical circuits. The combination of these principles showcases how real-world applications can be built from fundamental scientific concepts.